Shunt voltage reference as comparator might come in useful. What I have here at the moment is an AZ431L shunt current reference, internal reference voltage of 1.24 volts. These little thingies, they are basically knockouts of the same 431 Texas Instrument part, but cheaper. I have my input voltage. I go back in a second here. Input voltage I have, I think it's 470 ohm, a resistor here, and a load resistor of 1K. Here you have it in all its glory. So really not much to see. Yeah, the blob is here. There's my 470K. Here to the ground is my 1K resistor. And yeah, what these things can do is astonishing. I mean, this is my input voltage, and I can, yeah, do a lot to it. And yeah, also dial it down, and my output voltage here stays constant. Okay, yeah, nothing happens. And within reason, yeah, don't exceed the operations parameters of the thingy here. And of course, if the voltage drop across your resistor here gets too big, because the input voltage or the difference between input voltage and output voltage gets too small, then the load gets too high. Yeah. So within reason, within parameters, these things work just fine, and I can also pull the load resistor here, and it almost does nothing. So they are not perfect. I mean, here we're talking here about hundreds of a volt. What is actually changing 200ths of a volt. So 0.2%. And yeah, input voltage the same. So pretty stable. They are called adjustable shunt voltage reference for a reason, because they have their reference pin, which I currently shorted to the cathode, on a third pin. Otherwise it would just be a glorified Zener diode with a fixed Zener voltage, or reference voltage in that case. And what you can do is simply take a potentiometer or trim pot, for example. Forget about this one, and then the whole thing would be adjustable. Let's just do that. So I built in my potentiometer, which is 500K, into the circuit. The reference input is really only drawing a microamp or so, or half a microamp. Currently the potentiometer is turned completely to the left, so basically we have the same arrangement as before, but for another additional 500K as load to ground. And yeah, I can change the input voltage. Yeah, nothing happens. I can change the load. Nothing happens. And for further reference, I will remove now the load. It's just in the way. But what happens when I turn now the potentiometer to the right? That is towards ground. Then I suddenly have a voltage divider, and I can increase. Let's go here with the input up to 10 volts. That's a nice value. I can increase the output voltage. Up to 10 volts. Cool, huh? And of course, whatever value I choose here, that value is also stabilized. So if I now play with my input voltage, okay, yeah, within reason, my output voltage stays the same. These are all basically run-of-the-mill standard circuits you find in every datasheet for such a voltage reference. But there is usually a third test circuit for I off. If I connect my reference output to ground, this thing here will shut off, and we can try that. I take my reference input and simply, input voltage, output voltage, put it to the ground rail. Input voltage equals output voltage. The voltage reference clamps up completely. So the question is, how do they do that and how do they work internally? These are basically the innards of such a adjustable shunt voltage reference, and I think Texas Instruments put such a graphic to their datasheet. So what you basically have, looking just at that part, you have your V in, then you have your external resistor. Yeah, that was my 470 ohms. And then you have a transistor going to ground. And if you control that transistor appropriately, you can have controlled voltage at your output simply by increasing or decreasing the current through the transistor and thereby decreasing or increasing the current drop through the resistor. So we have an op-amp here, and that is simply connected via the internal 1.24 volts voltage reference, and that's a fixed voltage reference. That goes into the inverting input, and the ref pin is simply the positive input of the operational amplifier. And in this circuit diagram I can show you everything, because if I turn down the pot to the ground side, so basically then we have connected the plus, the non-inverting input of the op-amp directly to ground. So we have 0 volts in, and we have constantly 1.24 volts into the inverting input. So the op-amp will shut down the transistor and no current is flowing here, and then we have V in equals V out. That was that third reference circuit I showed you, that one here. And if we turn the potentiometer all the way up, we have basically our initial circuit, that is the reference pin, is connected to V out. And what does the op-amp do in that case? He tries, because he then has a feedback loop, see? To get both voltages, input voltages, to be the same. And that's 1.24 volts. So he will drive open the transistor until the voltage drop over the resistor is big enough so that only 1.24 volts are left here. Left here means also left here, 1.24 volts. And anywhere in between our potentiometer, or now we can say a potentiometer or two resistors, will work as a voltage divider. So for example, if I have 2K pot in the middle position, I have 1K here, 1K here. We set here as basically no current flowing, a microamp or so. Then to have 1.24 volts here, to make our op-amp happy, we need 2.48 volts, 50-50 voltage divide here at our output. The question arises, what happens if we break up this feedback loop? What if we cut this line, and here I got ahead of myself, and do something like that? Then the op-amp has no longer the capability to, in a feedback loop, to influence the input voltage on his non-inverting input through modulating the current here in the transistor. There is no feedback loop. What we then have is a comparator. An op-amp, without feedback loop is a comparator. And with an internal 1.24 volt reference. So he compares the voltage at the input here with the 1.24 volts. If it's smaller, it will shut off the transistor. If it's greater, it will shut on the transistor. Let's try that. So I dialed down the voltage to 5 volts. I'm now measuring here the input voltage to the reference pin, and our potentiometer is now simply set up between the positive rail, 5 volts, and ground. So I have the potentiometer now again completely over to the right, so basically connecting the reference input to ground, and the transistor is completely clamped up and we are at 5 volts, which is incidentally also the input voltage. Now watch if I increase that and approach 1.23, 1.33, and the transistor opened up, and we have now a voltage drop of 4 volts. Obviously the transistor didn't open up completely. We have still here 1 volt that is dropped over the voltage reference, and I will tell you the reason for that in a second. But if we increase now further the voltage, you see everything seems to be stable until we reach a certain point. 1.7, 2.0, and oh, look at the ammeter, what the ammeter does. Something goes very, very wrong. 2.0, Choo! What the hell is happening here? Choo! And you see the transistor is clamping up a little bit. So we have 2 effects here. First one, if we go over 1.24 volts, we cannot open up the transistor in the voltage reference completely. And if we go even further, at some point, weird things happen. And we are suddenly drawing current, a whole lot of current. So first of all, there are some traces missing here. That op-amp has, of course, supply voltage. And that supply voltage is basically the voltage we have across the voltage reference. And of course, at some point, if the voltage here, and we were at the end here at 1.0 volts, at some point, if that voltage gets too low, we cannot pass enough current through whatever happens here in the op-amp, through the base of the transistor and out again of the device, to drive that transistor fully open. I mean, you have obviously here the drop across that transistor diode of 0.6 volts, and you have some drops here, so yeah, there's a limit. The second thing is more of a black magic, and yeah, we have to have a look at the data sheet for that. If you look at the absolute maximum ratings for the device, There's of course your maximum voltage you can put across it until you have a breakthrough, and your maximum cathode anode current, which is negative to plus 100 milliamps, because obviously this protection diode can take up 100 milliamps, no problem. And but you also have this I reference input current range 10 milliamps. Why 10 milliamps? I mean, the reference current, and I talked about that before, reference input current is deemed to be very low. So typically 1.15 milliamps to 1 microamps. These are microamps. Yeah, I told you some microamps, it's even sub-microamps, so maximum 0.4 microamps and typically 0.15 microamps. But these conditions only apply when you operate the whole thing within its intended purpose. And intended purpose in that case means having the 1.24 volts here and 1.24 volts here. So the internal circuitry can work as intended. When we drop the voltage across the whole device and then suddenly have a high input voltage here, what we have is a positive voltage from this pin to this pin and from this pin to ground. That pin is in potential higher than our anode and cathode pin. And so we end up having some big current going into the reference pin, and obviously over 10 milliamperes, probably destroying something in here. Yeah, there's a remedy for that too, and that would be simply to put another resistor in here, just to limit the current to the allowed 10 milliamps. The other thing, I mean resistor here, of course, is if you have here a real voltage divider with two resistors, and it's dimensioned that there can never be more than 10 milliamps through here, then that's also okay. So you do not need necessarily a current limiting resistor here. Let's see how this actually performs on a real signal, on a real analog input signal, and what the output signal here is. What's all this then? I'm using the 1 kilohertz calibration output from the oscilloscope to drive a little NPN transistor to amplify the signal because it's quite high impedance. And then I have an RC element here to deform the rectangle to something like that. This goes to 100k potentiometer, so I can adjust the level of the distorted signal, and then we feed that into the reference input of the shunt voltage reference. And then we are measuring the output signal, which should be a rectangle again. This is my yellow amplified rectangle. This is my, after the RC element, my distorted rectangle. And this is the pink curve, the output of the potentiometer going to the reference input. And you see, if I dial that down, I'm turning the potentiometer right now, we go to the output blue to the high level. And if I cross here the 1.24 volt reference, we get converted back at the points where we cross 1.2 volts to a rectangle again. And yeah, if I increase the level, you can also see at some point this curve will flatten. Yeah, because then we're drawing suddenly a whole lot of current. If we talked about that, that is a critical voltage where input stage of the op amp somehow breaks down and we have to limit the current, which I don't do at the moment. And then we're drawing quite a high input current instead of less than a microamp. If I turn that further up, you see how the load from the reference input, the current flowing into the reference input, actually is clipping the curve. And if I continue that game, you see that also my RC element now gets a significant load. But as long as we are below that 1.5 volts or what it was, we are safe and can generate a nice almost rectangular curve. Now this is all happening at 1 kilohertz. So these voltage references are in that respect not really fast. So you won't be able to use them in 100 kilohertz range or even 10 kilohertz. Playing around with the thing so far was fun, but now I have a practical application for you. So what we have here is a Watchdog. Yeah, that's all. So we still have the amplifier stage here. So I have a nice 5 volt rectangle curve. Yeah, probably you could source it from a microcontroller, for example. So our Watchdog circuit starts here. We take our rectangle curve, we have current limitation. This would be at 4.7K. Worst case, roughly a milliamp is going through here. That's good enough for any microcontroller output. We go through a 100 nanofarad resistor and through a diode, and we charge up a 10 nanofarad resistor. This resistor is charged this way. And it's very rapidly. I mean, 10 nanofarads, and this resistor is 10 times higher, and we have 1 milliamp. Yeah, it's full in a jiffy. And as soon as our input signal goes low on this side, current cannot flow back here, but it's discharging. And I make the second cycle in red. Is discharging through the reference input with 1 microamp, at least if the voltage here is low enough. You remember this is fairly high impedance here, the reference input. It's basically the input of an op amp. If we raise the voltage too much, it breaks down, and we have to limit the current, which is the case through this resistor. So maximum 1 milliamp will go in here through the charge cycle. So high we charge, low we discharge. And we have here a pure AC coupling. So if the charge current goes through this capacitor, it will get positive here and negative here. And the discharge for this resistor is simply this path through this diode, and then here. This is both ground, but then we have here when the capacitor is charged up, negative, positive. So it's its own power source, its own battery. It's discharging through ground. of course, the output signal, as long as we are here over the 1.24 volts, this will open up and we have here low output. But as soon as no signal comes through, that capacitor is no longer charged. It will slowly discharge here through the reference input. And as soon as we are below 1.24 volts, this will clamp up and our output will go high. And this is exactly, plus the AC coupling, that's important, what you want from a Watchdog. Let's have a look at the oscilloscope. This would be normal operation. We have here our rectangle wave, our input or our output from the microcontroller. This is the voltage across our small 10 nanofarad capacitor, and you see it's coming here in discharged or almost discharged, and then it's very quickly charged. Our AC coupling was through a 100 nano capacitor with a 4.7K, so roughly 1 milliamp charge current. So the 10 nano is charged up very quickly, and then it slowly, with 1 microamp or roughly 1 microamp, is discharging through the reference input of the voltage reference. And during this phase we have kind of a voltage limiting. This is not fully charged up because at some point, and I should mention the scale for the pink curve is different. It's 500 millivolts per division, so we are here at 2 volts roughly, and this is 1.5 volts. If we approach that breakdown voltage of the reference input, the voltage is clamped down and the current is limited through that 4.7K resistor. So charging, we should say that at some point there's also a current of 1 milliamp shunted here through the reference input. What happens if we take away the signal and go high impedance there? It's discharging at some point. The input goes high. Yeah, I will pull the appropriate wire on the breadboard about now. The voltage across our capacitor goes to 0, it's discharged, and our output goes to high. I'm now connecting the input of our Watchdog to ground. You can see that the capacitor is drawn even a little bit lower. And now I'm connecting the input to the 5 volt rail. Let me go to negative again, and now to the 5 volt rail, so you can see that nice effect. Choo! So for a very short time we are charging, and yeah, you probably didn't see it, but our output goes low for a very short time. But either if I be high impedance on the input, or I'm low on the input, or 5 volt on the input, it doesn't matter. As long as I don't have a regular signal, our Watchdog will go high. That's exactly what you want from a Watchdog. As soon as the defined signal is gone, and it can be gone in any way, yeah, this can be high impedance, this can be constantly low, or this can be constantly high. Our Watchdog should bark. There's a little problem because most reset inputs are inverted. They need an active low. There's a solution to that, also with just these parts. But before that, I want to show you what I had in mind with the Watchdog. What I had in mind was simply an LED lighting up as soon as my Arduino, in this case, yeah, I need that for a project, my CardLink UV exposure unit controller. As soon as my Arduino hangs up or something goes wrong, I want a red LED to go on. And if I cut now my square wave signal from the, I always say rectangle, square wave signal from the simulated controller, the LED lights up here. As soon as I reconnect it, signal is there again, it's off. But I told you, you want low reset output. We can do that too. Here you have your Watchdog with an active low reset output. And the only new part here is that 1 meg resistor, which is slowly trickle charging our 10 nano capacitor. Initially, the 10 nano capacitor is at 0 volts, so we have 0 volt input here. So the thing clamps up and our reset output is high, that is inactive. It's slowly trickle charging, and as soon as we hit the 1.24 volts here, this opens up and our reset goes low. So that's trickle charging. So discharging this resistor regularly through the square wave happens again through our now inverse direction diode when our rectangle signal goes low. AC coupled, of course, so if it's constantly low, that won't work for long. And this resistor here is discharged. He's acquiring here charge plus minus in the discharge cycle for, I said resistor, capacitor, through this diode. So if we are here high, so we have plus, we have minus, and we have plus, so we assuming this has been charged up to 5 volts, we have double the voltage here. So we have 10 volts here and it can discharge here to the 5 volt rail. And that's all. And as you can see on the oscilloscope, in normal operation, our 10 nano capacitor is slowly charged up through our 1 meg resistor, and then as the square wave goes low, it is discharged, and then the cycle continues. And as soon as I disconnect, our output goes to low, 1 volt low, which is good for 5 volt CMOS logic or 5 volt microcontrollers. Won't probably work really good in 3.3 volt logic. I have another application for you with even less parts. Before that, just a little addendum. Depending on your microcontroller, you might want to add or not AC coupling here. Depends what your microcontroller does if he gets a constant low signal here. The simplest circuit possible with this is a key debouncer. So you have here your usual bouncy switch. In this case I have here 1 meg resistor, my 10 nano capacitor, and of course if I close here, the capacitor is charged up through that 1 meg resistor, and the voltage slowly rises until it reaches 1.24 volts, and then this opens up and our output goes low. So the output in this case is an active low output. So it's low when the switch is closed. If the switch opens again, same game as last time. The 10 nano is slowly discharged through the reference input of the voltage reference. And this is all of the circuit. So my switch, I took a really lousy switch, my 1 meg resistor, my 10 nano capacitor, and there in the back you probably can't see it, but there's a 1K resistor somewhere hiding, and my voltage reference. And this is when you capture the result on the oscilloscope. So the yellow line is the voltage just between the switch and the 1 mech resistor, and you see it's bouncy like hell. Here's the voltage across our 10 nano resistor, which is also not very stable, and this is the signal we're getting out. A really, really nice transition.